In this video, I'm planning on first talking about problem-solving techniques, and then I'm going to do an example problem and show you how you would apply these techniques to an actual problem. So it gets the problems in thermodynamics, and then also as you continue through engineering courses, get pretty complicated to set up. Like basically they'll have a lot of parts, and so if you follow a certain technique, or basically a set of steps to solve your problems, you're going to get them set up correctly most of the time. The hard part with these problems is usually getting them set up correctly. The easy part is plugging in numbers and solving them. So you want to make sure you get them set up correctly. So the first step is to read the problem, and that seems obvious, but a lot of times it can be tempting to start setting up a problem without fully reading it. So you want to read the problem, and it might be helpful to state the problem in your own words. So basically with that, make sure that you know what it's asking for. So for instance, if the problem says that it's adiabatic, you might just write down that means there's no heat in or out. So just make sure that you know what the problem is asking for and that it makes sense. One thing I always do when I solve these sorts of problems is I write down the problem. Like when I'm doing if I'm working through a problem, I'll write down the actual problem on my paper, and that helps you as you go forward, because if you need to go back and reference the problem, you know what the problem was that you were solving. If you only have the answer written down or a few steps written down, that's not going to help you study later, because you won't know what the problem is that you solved. So write the problem down. You can also copy the problem, like photocopy the problem or print it off out of your book. So then you just have the problem statement on a page, and then just solve the problem on that page. So write down the knowns and unknowns. So write down everything that you know. So like if you know T1, write that down. If you know T2, P1, maybe you're solving for P2. So I always write down my unknowns with a question mark, just so it's really clear that's what I'm solving for. And then you want to identify any processes. So do you have heat or work in or out? Is it constant volume? Is it constant pressure? Like is P1 equal to P2? Is it isothermal? Is T1 equal to T2? Does your volume change? Like is volume 1 equal to volume 2? Things like that. So you want to identify, along with the information that's given, what's going on. This is also a good time to look up any data that you might need and write it down. So like if you're going to need a gas constant, if you're going to need specific heats, you can look those up. You might not, at this point, you might not know exactly what all you're going to look up, because that'll partially depend on what equations you're using. So you don't necessarily need to look those up now, but if you know what they are. So number 2, and this for me, this is usually actually combined with number 1, because I usually make a drawing as I'm writing down the information, but basically make a drawing of your problem. So in other words, if you have a piston cylinder, you're just going to draw a piston cylinder and then indicate your heat, indicate work, write down what you have in there. So if you have water, just indicate what you have in there. So make a drawing. That helps clarify what's going on. So number 3, this is probably one of the most important steps. Well, all steps are important, but it's really important to state your assumptions. And don't just have your assumptions in your head, actually write them down, so then it's really clear what your assumptions are and how you can solve your problem. So for instance, do you have an ideal gas? Do you have a stationary system? Like, can you assume that the change in kinetic energy is equal to 0? Do you have a do you have a large elevation change? If not, your change in potential energy is equal to 0. Is your process, do you have a quasi-static process? So just write down all of your assumptions, and you want to make assumptions because your assumptions basically make your problem, depending on what assumptions you make, it's going to make your problem easier to solve. So for instance, if you can assume that you have an ideal gas, you want to do that. Step 4, this is where you're going to identify the equations you're using. So identify equations. So are you solving the first law? Do you have an ideal gas? Do you have boundary work? Is it polytropic? So just whatever equations you're using, and as you go further into as we go further, you might be using even more equations, like do you have a mass balance? So this is where you just identify the equations that you're going to be using, and this step is actually what a lot of people start with, and I think it's better to go through these other steps first, like figure out what you're even solving for, what you already know, your assumptions, and then write down your equations. Step 5 is where you'll be looking up anything that you might need on the table. This step, you're going to be looking up your property data. You might do a PV or TV diagram, so you might do a PV or a TV diagram. This is where you might be looking up your constants. So I mentioned looking up some of these back here. If you know you're going to be using them, I don't think it hurts to look them up at the start when you're writing down all your information for the problem. But you might not know exactly what you need until you identify what equations you're using. So if you need to look up your property data, then this is where you would do it. Then you're going to plug everything into your equations and do your calculations. So calculate results. This should be the easy part. Setting up your problem is the hard part. So once you get your answer, you're not quite done once you get your answer. After you get your answer, you want to look at it and think about it. First of all, does your answer make sense? If it doesn't make sense, then you might have done something wrong somewhere along with your assumptions, or understanding what you were solving for. Check your units. If your units are wrong, then that's an indication that you did something wrong. And this is why it's really important to include units in your calculations, because if your units don't cancel out correctly, then you know that you did something wrong and you need to go back and check your equations. All right, so let's solve this problem using the method that we just talked about, and then I'm going to be really careful to use this method for problems that I solve from now on, just so that every problem is set up the same, because I really think the easiest way to do these problems is to approach them with the same steps. So then you're really, you end up with different equations for every problem, but you're setting them up the same. So for this problem, the first thing we want to do is read the problem and then figure out what's going on. So it says we have stainless steel ball bearings that have a diameter of 1.2 centimeters, and they're quenched in water at a rate of 800 per minute. It says the balls leave the oven, so I'm going to actually start drawing what's going on as I'm reading it. So we have an oven, and it says that the balls are leaving the oven, so I'm just going to draw this like that. And so they leave the oven, and then they're dropped into water after a certain period of time, which it gives. So just draw that like that. And So, and then it says we want to determine the rate of heat transfer from the balls to the air. So basically the balls are, after they leave the oven, they're in the air for a certain amount of time before they get to the water. And so so we kind of know what's going on. The balls are leaving the oven. They're in air for a certain period of time, and then they're dropped into water. And we want to determine the rate of heat transfer from the balls to the air. So basically we want to figure out how much heat is transferred from the balls to the air after they leave the oven before they're dropped into the water. So let's start writing down some of our information from the problem. First of all, it gives us the density of the balls. So the density is 8,085 kilograms meters cubed. And it also gives us the specific heat of the balls. And this is 0.480 kilojoules kilogram degrees Celsius. Whoops, this is kilogram. And so these were both given. We could look these up. It tells us they're stainless steel. So if it didn't give us the density or the specific heat, we could just look those up for stainless steel. It tells us that the diameter of the balls, I'm going to try and write a little bit bigger. The diameter of the balls is equal to 1.2 centimeters. And let's see, the temperature that the balls leave the oven, so I'm going to put that here just so it's on our drawing. So the temperature, and I'm going to call this temperature 1 for the balls. So this is the temperature that the balls leave the oven. This is 900 degrees Celsius. It also tells us that the temperature of the air is 25 degrees Celsius. And it tells us that the temperature 2 of the balls, so the temperature of the balls right before they drop into the water is 850 degrees Celsius, so that's right here. And then it tells us that there's 800 balls per minute leaving the oven and falling into the water. So we have a rate for the number of balls. I'm just going to put that this is equal to n dot. And what we're trying to figure out, I'm just going to summarize all of the balls. We're trying to determine Q from the balls to the air. So let's make some assumptions. The main assumption I'm going to make is that the change in kinetic energy is equal to the change in potential energy is 0. Well, it's not actually 0, but I'm going to say it's negligible. So the rate of heat from the balls is going to be a lot more than the change in kinetic energy. So we have a drawing. So we have our drawing. We have identified the unknowns and the knowns, and we have a physical sketch, and we've stated some assumptions. I'm going to also say that we're assuming constant specific heat for the steel. That was given, that was kind of given that we could just use the constant specific heat as an assumption. Now we want to identify our equations. So the equation that we're going to be solving for this is the first law. So we have Q minus W is equal to delta U plus the change in kinetic energy plus the change in potential energy. So this is the equation we're going to be solving. We already know that the change in kinetic energy and the change in potential energy are both 0 because we made that assumption. And there's also no work. So let's go back. We should have been really clear about what our system is. So our system is basically the balls. And we're just going to solve this first for one ball, and then we'll multiply it by the by the number of balls per minute. So let's just consider one ball. So there's no work into or out of the ball, but there is Q out. So work is 0, Q is out, so we have negative Q out is equal to the change in internal energy of the ball. So this change in internal energy of the ball is equal to the mass multiplied by U2 minus U1, and this is equal to m C sub p, so this U2 minus U1 is C, well, since we're dealing with a solid, I'm just going to call it C, and then T2 minus T1. So m C T2 minus T1. And then the only thing that we seem to be missing is so to solve this equation, we're looking for Q out. So Q out is equal to mc T2 minus T1. We weren't given the mass, so we need to calculate the mass. Well, we can calculate the mass because we know the density, and we can calculate the volume because we were given the diameter of the ball. So let's just go to the next page. And I'm going to rewrite this equation that we're solving here. And we're looking for the mass, so we can solve for Q out. So the mass of the ball is equal to rho v, so that's the density multiplied by the volume. So this is rho, and then the volume is pi d cubed over 6. So this is equal to, the density was given as 8085 kilograms meter cubed, and then the volume is pi the diameter of the ball was 0.12 meters, and then this is cubed divided by 6. So this is equal to 0.007315 kilogram. Now we have everything we need to solve for Q out. So Q out, and I'm going to multiply this by a -1. So I have negative Q out here, and I just want Q out. So this is equal to MC, and then T1 minus T2. So I just multiplied this by -1. That caused T1 and T2 to swap. So this is equal to, the mass is 0.007315 kilogram. The specific heat is 0.480 kilojoules kilogram degrees Celsius. And then T2 minus T1, or sorry, T1 minus T2 is 900 minus 850 degrees Celsius. So the kilograms cancel, degrees Celsius cancels, and we get 0.1756 kilojoules per ball. So we actually want Q dot, and I should have specified that back on the problem. So we want the rate that the heat is being transferred from the balls to the air, and we want to include all of the balls, not just one. So this calculation that we just did is the kilojoules per ball, so that's the amount of heat lost for one ball. So Q dot is equal to Q out, which we just calculated, multiplied by N dot. So remember, N dot is 800 balls per minute, and that was given in the problem. So Q dot is equal to 0.1756 kilojoules per ball multiplied by 800 balls per minute. So balls cancel, and this works out to 140.5. Rewrite this. So 140.5 kilojoules per minute. And then let's actually convert this to seconds. So 1 minute to 60 seconds. So Q dot is equal to 2.34 kilojoules per second, which is 2.34 kilowatt